Welcome to this video on matrix inverses. Matrix inverses are really helpful to know how to work with because often in linear algebra you're trying to work out the solution to some equation, and you need to use inverses to get rid of matrices that you don't want from the equations. And the only way to remove them is by multiplying by the matrix inverse. So let's take a look at what they are more abstractly, how to work with them algebraically, and then also how to calculate them directly using augmented matrix methodology. Okay, so first of all, the identity matrix is equal to the square matrix here with ones down the leading diagonal and zeros everywhere else. And A times I is equal to A, I times A is equal to A, I is equal to the transpose of itself, i.e. that it's symmetric. And the inverse definition is defined like this. Let A be an n by n square matrix and I denote the n by n identity matrix. A is invertible or non-singular if there exists some matrix B such that A times B is equal to B times A, which is equal to I. Therefore, we define B as the inverse of A and have this A to the power of -1, which is a way of defining and signaling that this matrix is the inverse. Okay, so we have some inverse rules. Maybe just to make it simpler, we'll look at it one step at a time. So the inverse of an inverse is equal to itself. A multiplied by A inverse is equal to I. So the inverse of A inverse is A. So if you look at it from the perspective here of thinking about, well, what's the inverse of B? Then A is now satisfying that. So the inverse of the inverse is itself. That's how we get this rule here. We know that if AB is equal to I, BA must be equal to I as well. And if AB is equal to I and AC is equal to I, B is equal to C. So inverses are unique. If you find one on the right or on the left of A, you know it's also the other side of A. And then if you find two inverses to A, they must be equal to each other because there's only one unique inverse for a matrix. Okay, this one here is really important. The inverse of A multiplied by B is equal to B inverse A inverse. So let's actually just derive that together. This one's worth doing together. So AB, what I am telling you is true, is that the inverse of this is equal to this. But let's actually use linear algebra to show that this is true. So what we'll do is we will have AB multiplied by B minus 1, A minus 1. Sorry, that should be minus there. And we're trying to show that is equal to the identity matrix. And if we work from the left-hand side and get that equal to I, we've shown that this is clearly the inverse of this. Okay, so the thing about matrices when you multiply them together is you must maintain order from left to right, but you can choose to put the brackets where you would like. So let's start by putting the brackets around B's and multiply them with each other first. And because B minus 1 is the inverse of B, that gives us I like this. And then A multiplied by I is just A. And then now we're left with this. So we get I because that's the inverse of A. And we've now shown that this is the inverse of this. Easy. Okay, the other one that I will derive here is showing that the inverse of the transpose is equal to the transpose of the inverse. So let's derive this one together as well. Okay, so to do this, let's first start with this. So we've got A multiplied by A inverse is equal to I, and we're trying to show that the inverse of the transpose is equal to the transpose of the inverse. So if we take the transpose of both sides, we have, do it like this. We have this, and I transpose is just equal to itself. So that's equal to I. And then when you take transpose of two matrices multiplied by each other, you switch the order. So we've got A minus 1 transpose A is equal to I. So A transpose is equal to I. Okay, and that means that A to the minus 1 transpose is the inverse of AT. So the way that I'm looking at this is that this is the inverse of this. So we've actually shown now that here A to the minus 1t is the inverse of AT. Because when they multiply together to give you I, we know from above that makes it the inverse, and that this inverse is unique. So you can see the summary here. Thus, A to the minus 1t is the inverse of AT, and so we can write that out as A to the minus 1t is equal to AT to the minus 1. That's what this means. All right, so that's some linear algebra rules for us to look at. Second thing we can do in this video is actually working out how to calculate the inverse of a matrix in terms of the specific numbers directly. So less the linear algebra part and more just the calculation of the inverse. So if you're dealing with a 2 by 2 matrix, you do 1 divided by the determinant multiplied by a slight modification of the order of the elements. But this method I'm going to show you here is what you do for higher order matrices like a 3 by 3 or more, where you can use Gaussian elimination or specifically Gauss-Jordan reduction to work out what the inverse is. Okay, so A multiplied by A minus 1 is equal to I. Our goal is to find the inverse of A given A. So what is the inverse to the matrix A? And the way that we do that is we have A and then I on the right, and we perform elementary row operations to give us I on the left and whatever is left on the right. And according to this method, whatever's left on the right is the inverse of A to the minus 1. So if you start with A here on the left, and then you rearrange things, you will get a inverse as whatever is there on the right using this method. And then that's it. So we can take a look at an example of this. If we have A here equal to 1, 2, minus 1, minus 2, 0, 1, 1, minus 1, 0, and we're trying to find the inverse of A, then we can use this Gauss-Jordan reduction to work out this inverse. So collecting this together in our augmented matrix, we have the matrix A on the left and the identity matrix on the right. And then we now start applying elementary row operations to this left-hand side to get it into the identity matrix. And from a quick big picture overview, eventually we're going to get this on the left, and then this on the right is our inverse of A. And specifically, if we just take a look step by step, we can start off by getting zeros on the left-hand side because we need those for this identity matrix. And we're just being very careful to make sure that whatever we change on the left is being changed in the same way on the right. So when we add 2 of row 1 to row 2, we're adding 2 of row 1 to row 2 on the right, which gives us this 2 here. And then subtracting 1 of row 1 from row 3, and then we get this here. And then next, we want to get rid of this one here. So we can take a combination of row 2 and row 3 to make it sum to 0. So 4 times row 3 plus 3 times row 2, and together that will give us 0 there. And then we follow through again on this bottom row here. Next, we want to get rid of zeros above this one here. So we use this one to eliminate this. And that's what you can see with our zeros here. Then we can divide by 4 in the middle because we need to have 1, 1 in the leading diagonals. And then we can use this to get rid of this, which is our final step here. And that's it. Once you've done our transformation to give us the identity on the left, whatever's left on the right is A minus 1. And so that means that matrix A up here multiplied by this will give us the identity matrix. Alright, so thank you for watching this video on inverses. Hopefully you found it helpful both in terms of linear algebra directly and calculating inverses that are non-trivial using the Gauss Jordan reduction method. Alright, thanks for watching.